You are completely wrong about past and future. You probably think the past is fixed and the future is open. You imagine that yesterday's events determine today's choices, and today's choices will determine tomorrow's events. You think time flows in one direction, from cause to effect, from past to future. But that isn't how time works. That's just a temporal illusion, a chronological prejudice that has absolutely nothing to do with how reality actually operates. Most people walk around with this linear idea in their heads that causation flows forward through time. They picture the universe as a cosmic domino sequence, where earlier events knock over later events in a neat, orderly progression. They think the future is uncertain because it hasn't happened yet. But here is the problem with that beautiful assumption. Time symmetry doesn't care about your intuitions. Past and future are not fundamentally different. And according to cutting-edge physics research, the future might be determining the past just as much as the past determines the future. The truth is much stranger, much more symmetric, and honestly a lot less intuitive than forward-flowing causation. Physics equations don't distinguish between past and future. Time doesn't have an inherent direction built into the fundamental laws of nature. And if you think tomorrow's events can't influence today's measurements just because they haven't happened yet, you are about to discover some very uncomfortable truths about the nature of time. Dr. Sabine Hossenfelder has been investigating something called future input-dependent quantum mechanics, the idea that quantum measurement outcomes are influenced not just by past conditions but by future conditions too. This isn't science fiction. This isn't philosophical speculation. This is serious theoretical physics research aimed at solving one of quantum mechanics' most persistent problems. Hossenfelder's approach emerges from her work on superdeterminism, but with a temporal twist. If the universe is superdeterministic, meaning everything is correlated through hidden variables that trace back to the Big Bang, then why should those correlations only flow forward in time? Why shouldn't future events be correlated with past events through the same hidden variable networks? Time symmetry in physics, Hossenfelder explains in her recent papers, suggests that future measurement settings should be just as relevant to current quantum states as past preparation procedures. Think about what this implies. The decision you make tomorrow about which quantum measurement to perform might already be influencing the quantum state of particles today. The choice you haven't made yet could be determining the experimental results you're observing right now. To understand Hossenfelder's radical proposal, we need to examine what she calls the temporal measurement problem in quantum mechanics. Standard quantum mechanics assumes that measurement outcomes are determined by the quantum state at the moment of measurement, plus some fundamental randomness. You prepare a quantum system, let it evolve according to Schrödinger's equation, then measure it. The measurement reveals one of many possible outcomes, apparently chosen at random from the quantum probability distribution. But Hossenfelder asks, why should the randomness be fundamental? And why should only past events influence the measurement outcome? Her alternative is startling. What if quantum measurements aren't random at all? What if they're determined by correlations between past and future events? What if the choice of measurement outcome depends not just on how the quantum system was prepared, but also on what measurements will be performed on related quantum systems in the future? This isn't about faster-than-light communication or violation of causality. It's about recognizing that time-symmetric correlations could extend in both temporal directions from any given moment. Just as past events can be correlated with present measurements through hidden variables, future events could be correlated with present measurements through the same hidden variable networks. If superdeterminism is correct, Hossenfelder writes, then the statistical independence assumption fails not just for spatially separated measurements, but for temporally separated measurements too. Consider a quantum experiment performed today. Standard quantum mechanics says the outcome depends on how you prepared the system yesterday plus fundamental randomness. Hossenfelder's approach says the outcome depends on yesterday's preparation and tomorrow's related measurements connected through superdeterministic correlations that extend both backward and forward in time. The apparent randomness disappears when you account for both temporal directions of correlation. Hossenfelder and her collaborator Sandro Donardi have developed mathematical formalism for future input-dependent quantum mechanics. Their equations modify standard quantum theory to include what they call future boundary conditions, alongside the usual initial conditions. In normal quantum mechanics, you specify the initial state of a system and let it evolve forward in time according to Schrödinger's equation. In Hossenfelder's approach, you specify both initial conditions and final conditions, what the system will be measured to be in the future, and solve for the probability of current measurement outcomes. This creates what they call a temporally non-local theory. Just as Einstein worried about spatial non-locality in quantum entanglement, this theory involves temporal non-locality, where future events influence past events through hidden correlations. The mathematics is surprisingly elegant. The future boundary conditions enter the quantum equations in exactly the same way that past initial conditions do, preserving time symmetry while eliminating the need for fundamental randomness. But the implications are mind-bending. It means that when you perform a quantum measurement today, the outcome might depend on quantum measurements that will be performed next week, next year, or even next century, as long as those future measurements are correlated with today's experiment through the underlying superdeterministic structure. This doesn't violate causality because information isn't traveling from future to past. Instead, both past and future measurements are constrained by the same timeless correlation pattern that was established at the beginning of the universe. Think of it like a cosmic jigsaw puzzle, Hossenfelder explains. Each measurement outcome is a puzzle piece that has to fit with all the other pieces, both past and future. The pattern of the complete puzzle determines what each piece looks like. This raises a disturbing question about free will and temporal agency. If future decisions influence past quantum measurements, what does this mean for the idea that you freely choose what to do tomorrow? Hossenfelder's answer is characteristically direct. Free will, as commonly understood, is a temporally local illusion. You think you freely choose what quantum measurement to perform tomorrow. But according to future input-dependent quantum mechanics, that choice is correlated with quantum measurement outcomes happening today. Both your future decision and today's quantum events are part of the same superdeterministic pattern. This doesn't mean you don't make choices. It means your choices are not temporally isolated events. They're part of a time-symmetric correlation network that extends both into the past and into the future. The feeling of free choice, Hossenfelder argues, comes from our limited temporal perspective. We experience decisions moment by moment, but the universe sees the entire temporal pattern at once. Think about what this means for causation. Normally, we say past events cause future events, but in a time-symmetric universe, future events also cause past events through backward temporal correlations. The word cause becomes misleading because it assumes temporal direction that the underlying physics doesn't support. Instead of cause and effect, we have temporal correlation. Instead of free will, we have temporally extended patterns of superdeterministic constraint. Your decision tomorrow and today's quantum measurement outcomes are both expressions of the same underlying temporal structure. This might sound fatalistic, but Hossenfelder argues it's actually more empowering than traditional views. You're not an isolated decision-maker buffeted by random quantum events. You're part of a coherent temporal pattern that extends across the entire history of the universe. Can future input-dependent quantum mechanics be tested experimentally? Hossenfelder believes it can, though the experiments would be extraordinarily challenging. The key insight is that if future measurements influence current quantum states, then quantum correlations should violate standard quantum mechanical predictions in specific, measurable ways when the temporal correlations are taken into account. Hossenfelder proposes experiments involving quantum measurements performed in carefully controlled temporal sequences. If future measurements influence past quantum states, then the statistical distributions of measurement outcomes should show subtle but detectable deviations from standard quantum predictions. The problem is that these deviations would be very small and would require extraordinary experimental precision to detect. You'd need to measure quantum correlations across multiple timescales while accounting for all possible sources of noise and bias. More ambitiously, Hossenfelder suggests that future input effects might be detectable in cosmological observations. If the quantum measurements performed by conscious observers throughout the universe influence the quantum state of the cosmic microwave background, then there might be subtle signatures of this temporal non-locality in the patterns of early universe radiation. The cosmic microwave background, she speculates, might contain information about the future history of quantum measurements throughout the observable universe. This is highly speculative, but it illustrates how far-reaching the implications of future input-dependent quantum mechanics could be. If consciousness and measurement are cosmic phenomena that influence the quantum state of the universe, both backward and forward in time, then the boundary between physics and cosmology dissolves. Many physicists are skeptical of Hossenfelder's future input approach. They argue that it violates our fundamental understanding of causation and makes physics unnaturally complicated. The strongest objection is that future input-dependent quantum mechanics seems to require a block universe view of time where past, present, and future all exist equally. This conflicts with our experiential sense that the present moment is special and that the future is open. Hossenfelder's response is that our experiential sense of time might simply be wrong about the fundamental nature of temporal reality. Physics has repeatedly shown that our intuitions about space and time are unreliable guides to how reality actually works. Another objection is that the theory seems to make prediction impossible. If future events influence current measurements, how can you predict anything without knowing what will happen in the future? But Hossenfelder argues this misunderstands how prediction works in a superdeterministic universe. You don't predict the future based on present conditions. Instead, you calculate the temporal correlation pattern that connects past, present, and future events. Prediction becomes a matter of finding solutions to time-symmetric equations rather than evolving initial conditions forward in time. The most serious objection is that future input-dependent quantum mechanics might be unfalsifiable. If the theory can always explain any measurement outcome by invoking appropriate future correlations, then it might not make genuinely testable predictions. Hossenfelder acknowledges this concern but argues that the theory does make specific predictions about the statistical structure of quantum correlations across time. These predictions differ from standard quantum mechanics in ways that could, in principle, be measured experimentally. So here you are, probably thinking about time differently than you did 10 minutes ago. You started believing that the past determines the future in a simple, linear progression. Now you know that temporal causation might be far more symmetric and interconnected than human intuition suggests. Sabine Hossenfelder has shown us that time symmetry in physics demands that we take future input correlations seriously, that the apparent randomness in quantum mechanics might disappear when we account for temporal correlations extending in both directions, that free will might be a temporally local illusion, masking a deeper pattern of cosmic temporal correlation. Does this make the future less open, less full of possibility? Hossenfelder would say it makes the future more connected to the present and past than we ever imagined. Your decision tomorrow about which quantum measurement to perform might already be influencing quantum experiments happening today. The choice you think you'll make freely next week might be part of a temporal correlation pattern that extends back to the Big Bang and forward to the end of time. You're not an isolated temporal agent making random choices in an uncertain future. You're part of a temporally extended pattern that connects all moments in the history of the universe. Your future decisions and past experiences are woven together in ways that transcend ordinary notions of cause and effect. The universe doesn't just remember its past. According to Hossenfelder's research, it might also remember its future. And you, with your sense of flowing time and open possibilities, are how the universe experiences this temporally symmetric reality from the inside. Time isn't what you think it is, but it might be far more beautiful than anything human intuition could imagine.